Hello guys, today we are revising the physics paper from May-June 2020. This is our paper 2 questions, which are AS level structured questions. This paper is written by the AS level students and the A level students who are making one sitting. So let's get started. Now let us move to question number 1. Define velocity. This one is very easy, and you can define velocity using an equation. You can define velocity using words. If you use words, I think the best would be to say velocity is rate of change of displacement. This is a very straightforward definition that we have learned since we were in our IGs. We can also use an equation to define velocity. It's very acceptable. We can say displacement divided by time. I think it's a good idea to put a delta, change in displacement, over change in time. That is our velocity. A common mistake here would be to use the word distance. Please do not use the word distance when you are required to define velocity, because distance does not include direction. Alright, let's look at the second one, a very common type of a question where they ask you to calculate uncertainty. Let's see how we can solve that one. The speed v of a sound wave through a gas of pressure P and density ρ is given by the equation. We have our equation where K is a constant that has no units. An experiment was performed and the following data was obtained. Let's move to the question. Use data from Fig 1.1 to calculate K. Okay, I would say the most important skill that is being tested here is your understanding of how to make a variable a subject of the formula. So how can we make K the subject of the formula? Firstly, we are going to square both sides. So we have V squared is equal to square root of K P divided by ρ. And I'm actually taking a very long route. We don't really have to go through all that trouble. Now, if we are squaring the square root, it means the square root and the square, they are going to take out each other. So we'll end up with V squared is equal to Kp divided by ρ. Now we are going to divide both sides. Okay, I think let us multiply both sides by ρ over P. We'll do the same, ρ over P, and the right hand side is going to look like this. Ρ will take out ρ, P will take out P. So we now have ρ V squared divided by P is equal to K. Now if we substitute the data that is given in the question into those variables ρ, V squared and P, we will definitely get our K. So we can say K is equal to ρ is 1.29, V squared is 3.3 times 10 to the power 2. This whole thing is squared, or divided by P, which is 9.9 times 10 to the power of 4. When you are working on a question like this, please make sure the units are SI units. For example, if our ρ was in grams per cubic centimeter, we were supposed to convert it to kgs per cubic meter. So please pay attention to the units before you just plug in the values. Alright, if we do that, we will have our answer as 1.4. 1.4, and we have been told that K does not have units, so we don't have to worry about that. So down here we will say 1.4. All right, use your answer in B item 1 and the data from Fig 1.1 to determine the value of K with its absolute uncertainty to an appropriate number of significant figures. Okay, so we are going to be calculating the absolute uncertainty, and we are going to present our answer to the appropriate number of significant figures. All right, so the important equations that we are going to need to use here, they are, we have an equation which says if A is equal to B times C, then fractional uncertainty in A is equal to fractional uncertainty in B plus fractional uncertainty in C. And we can also use the same equation if A was equal to B divided by C. So if A is equal to B multiplied by C, and if A is equal to B divided by C, this equation can be applied and it works very well. Another equation which is very important when we are working with uncertainty is suppose A is equal to B to the power of C. Therefore, fractional uncertainty in A is equal to C multiplied by fractional uncertainty in B. Well, these are the equations which you need to employ. Now, we have just seen that K is equal to rho V squared divided by P. So to get the fractional uncertainty in K, we are going to, let me get the bottom where there is more space. Fractional uncertainty in K would be equal to fractional uncertainty in rho plus fractional uncertainty in P plus 2 multiplied by a fractional uncertainty in V. These are the equations that we need to employ. Please just pardon me, I need to switch off this. All right. Now, in the data in the table is showing us the percentage uncertainty. The percentage uncertainty is basically equivalent to fractional uncertainty. So, 3% is basically 3 divided by 100. So, we are going to say this is percentage uncertainty and this is fractional uncertainty. It is as simple as that. So, let's carry on. Let me pick my bright color there. I think it is easier to see red. All right, so fractional uncertainty of rho would be 4 divided by 100 plus fractional uncertainty in P, it will be 2 divided by 100 plus 2 multiplied by fractional uncertainty in V, which is 3 divided by 100. These values, they are going to add up to give us 4, 6, 12. 12 divided by 100. So the fractional uncertainty in K is 12 divided by 100, which is 12%. Now I would like you to know that fractional uncertainty is equal to absolute uncertainty divided by the calculated value or the actual value. So now we can substitute this information and we can say the fractional uncertainty that we just obtained, which is 12 divided by 100, it is equal to delta K that we are calculating, the absolute uncertainty, divided by the actual K, which is this value here, 1.4. Therefore, delta K would be equal to 12 over 100 times 1.4. Okay, if we punch the values in our calculators, let me actually do that very quickly. 12 times 1.4 divided by 100. I am getting 0.168. This is the delta K that I'm getting. So now we need to show our answers to the appropriate number of significant figures. Theoretically, the appropriate number of significant figures, let me say generally rather than theoretically, the appropriate number of significant figures would be the number of significant figures which match the data that has the smallest number of significant figure in the raw data. So for K, we are going to look among the raw data there, and we can see 3.3 and 9.9, those are two significant figures. So K should be presented to two significant figures. Then uncertainty, if we look at the data which is in the uncertainty column, it is being presented to one significant figure. 3%, 2%, and 4%, that is one significant figure. So our value of K should be presented to two significant figures, that is 1.4, and our value of delta K should be presented to one significant figure, which is 0.2. This is the solution to our question number 1. Let us move to question number 2. A block X slides along a horizontal frictionless surface towards a stationary block Y as illustrated in Fig 2.1. Okay, the diagram shows us the relative positions of block X and Y. There are no resistive forces acting on block X as it moves towards Y. At time t is equal to 0, block X has a momentum of 0.4 kg meters per second. A short time later, the blocks collide and then separate. The variation with time t of the momentum of block Y is shown in Fig 2.2. Okay, so the graph is showing us the variation of momentum of the block which was initially stationary, which had momentum equal to 0. And all right, then we get to the question. So I just want to explain a little bit what is happening here. These two blocks, they form a closed system. It's not mentioned, but it's true. The surface is frictionless. Okay, it is mentioned here. We can also see it here. The surface is frictionless, and the forces like drag, air resistance, they are negligible in this situation. So the momentum of the system at the beginning is equal to the momentum of the block X. When these two collide, block X is going to transfer some of its momentum to block Y, and block Y is going to gain momentum according to the graph that we have just seen here. All right, the momentum of the system at the beginning should be equal to the momentum of the system at the end. That is the law of conservation of momentum. Now, with that said, let's get to our questions. All right. Define linear momentum. Very easy. This is equal to velocity multiplied by mass. You would remember mv, P is equal to mv. This is the simplest way to define linear momentum. Okay, use fig 2.2 to determine the interval over which the blocks are in contact with each other. Let's go to the graph and see when the blocks were in contact. So at the beginning, block Y was stationary right up to 60 milliseconds. Then it was hit by block X, causing the transfer of force from block, causing not a transfer of force, but causing a transfer of momentum from block X to block Y. So during this change in momentum, when block Y's momentum is increasing, this momentum is coming from block X because they are in contact with each other and X is exerting a force on block Y. So this is going to happen until we get to 100. So the time of contact is from 60 milliseconds to 100 milliseconds. We can write that down. 100 from 60, that's 40 milliseconds. All right. Use fig 2.2 to describe without calculation the magnitude of the acceleration of block Y from time t equal to that one up to 100, from 80 milliseconds to 100 milliseconds. All right, let's see what is happening from 80 to 100. All right, so we know that momentum, rate of change of momentum is directly proportional, or it is similar to rate of change of acceleration. From this equation, mv divided by t, that is the rate of change of momentum. If we say m bracket v over t, we can get ma. So the change in momentum, it looks exactly similar to the change in acceleration. Here we can see from 80 to 100, momentum is changing constantly. Therefore, our acceleration is constant. So we can say that our acceleration is constant. Then from t equal to 100 milliseconds to t equal to 120, momentum is not changing. So acceleration is 0. Acceleration will be 0 because our momentum is not changing. So we can say equal to 0 meters per second squared. All right. Use fig 2.2 to determine the magnitude of the force exerted by block X on block Y. All right. Let's go back to the fig that we should use, and we are going to say we can use the equation of impulse here, where Ft is equal to delta momentum, change in momentum. Sorry, I forgot the time frames, so let me just quickly check. From t equal to Okay, during the whole transfer of momentum, during the whole interaction, so the change of momentum, we can say F. Our time of interaction is 40 milliseconds, so F multiplied by 40 times 10 to the power minus 3 for milli is equal to change in momentum. Our change in momentum is from 0 to 0.5 kg meters per second. So 0.5 minus 0. Therefore, our F would be equal to 0.5 divided by 40 times 10 to the power minus 3. If we substitute these values, we are going to get, let's see, we will get 13 newtons, rounded off, 13 newtons. So the force that was exerted on block Y by block X is 13 newtons, and I think it is also important to notice that 13 newtons is the same force that was also exerted on block X by block Y according to Newton's third. So they are both exerting an equal force on each other. So we have 13 newtons there. On Fig 2.2, sketch the variation of the momentum of block X with time t from t equal to 0 to t equal to 160 milliseconds. So during the entire time, how did the momentum of block X change? Block X started with a momentum of 0.40 kg meters per second. So the momentum of the block was here. It maintained this momentum until it interacted with block Y. So the momentum from time equal to 0 to time equal to 60 was 0.4 kg meters per second. When these two interacted, the momentum at the beginning should be equal to the momentum at the end. So the momentum of the system at the beginning is 0.4 plus 0. 0.4 is the momentum of X and 0 is the momentum of Y, because we have been told that Y was stationary. The momentum at the end is equal to 0.5 from block Y on the diagram there, plus the new momentum of X. So let's just call it Px. If we shuffle our values around, we are going to see that P is equal to minus 0.1. So the momentum of block X, Px, the momentum of block X is equal to minus 0.1 kg meters per second. So after the interaction, we are going to have X with, so the interaction is going to stop at 100 milliseconds. Therefore, at this point, we have minus 0.1. So we will join these two. Then finally, we will have block X will continue with the same momentum right up to the end. All right, so this is the diagram that is expected for this question. Now to question number 3. The variation with extension X of the force acting on a spring is shown in the graph below. Okay, the spring of unstretched length and blah blah blah, everything makes sense. We start with a spring that is unstretched then we end with a spring that is stretched. We assume that this string is still obeying Hooke's law and it is not past the elastic limit. So a block of weight is attached, the block is then released, and assume the air resistance and the mass of the spring are both negligible. That's perfect. For the change in length of the spring from 0.4 meters to 0.72 meters, use Fig 3.1 to show that the increase in elastic potential energy in the spring is 0.64 joules. Alright. Increase in elastic potential energy. The energy that is stored in a stretched spring is equal to, let's say energy is equal to, first equation is 1 over 2k x squared, where k is the spring constant and x is the extension. We can also use the equation 1 over 2 fx, where F is the average force, that is maximum force minus minimum force divided by 2. We have already divided by 2 by the introduction of the half there. Then the X is the extension, so we can use that equation as well. Since our graph is starting from 0 on both axes, we can also take the area under the graph. This area under the graph is equivalent to the energy change which happens when you stretch a string. So let's use the area under the graph. Let me just check the points which we are using. So from 0.4 meters to 0.72 meters. Okay. From 0.4, this is the point when the length of the spring is 0.4, and let's see the point where the length of the spring is 0.72. So we say 0.72 minus 0.4. Sorry, 0.4 there. Let me just do a quick calculation there. 0.72. Sorry, 0.72 minus 0.4. We get 0.32. So our extension, we are talking about this point. Alright, so what is the force at that point? It is 4. Therefore, the area under that triangle, this area, is equal to 1 over 2 times force, which is 4, times x, which is what is the value of x? 0.32. Okay, there are joules. If we punch those values in the calculator, we will get 0.64 joules. And we have thus shown what the question required us to show. We have shown what the question required us to show. Okay, calculate the decrease in gravitational potential energy of the block of weight 2.5 newtons. Alright. Our block is starting at 0.4. Sorry, I want this one. Our block is starting at 0.4 and it is ending at 0.72. The change in height, delta H, is equal to, we calculated that and we found it to be 0.32 meters. Now we know that change in gravitational potential energy which is change in GPE, is equal to mg delta H. Our mg is the weight, so we can say weight multiplied by delta H. So if we substitute 2.5 for weight multiplied by 0.32 meters for delta H, we will get the change in GPE. So this is, we just punch in the calculator and we get 0.8 joules. So that is the change in gravitational potential energy. It's actually a drop in gravitational potential energy. I want to recommend you to use the delta notation because the question specifically asked for the change in. If you don't include the delta notation, you appear as if you are just calculating the gravitational potential energy at a particular point. So the delta in is very good for your notation. Alright. Otherwise, the decrease is 0.8 joules. There is no need to put a negative because of the presence of decrease. Alright. Use the information in A1 and your answer in item 2 to determine for the instant when the length of the spring is 0.72 the kinetic energy of the block. Alright, let's see our block and the answers which we have calculated. Alright, so at this point the block had GPE, which is GPE plus 0.8. When it dropped to the bottom, part of the gravitational potential energy which it was transferring to kinetic energy was actually taken by the spring. In other words, the spring is doing some work against the gravitational potential energy, against the kinetic energy which is increasing downwards. So we are going to have 0.8, which is the gravitational potential energy which was supposed to be transferred to be kinetic energy if there was no resistance. And we are going to subtract a part of the gravitational potential energy that was taken by the spring as the spring increased its elastic potential energy. That elastic potential energy which got to the spring or which increased in the spring is being taken away from this 0.8. So we are going to have minus 0.64, which is the elastic potential energy that we calculated. The difference between these two is going to be used to increase the velocity of our weight, which is going down. So 0.8 minus 0.64, this is the kinetic energy. So 0.16 joules. This is the kinetic energy of the block as it goes down at the moment when the height is 0.72 meters. Alright. So kinetic energy calculated. Then the speed of the block. The speed of the block is related by kinetic energy using the equation 1/2 mv squared, where m is the mass of the block and v is the velocity or speed of the block. This is equal to kinetic energy, which is Ke. Alright, now making v the subject of the formula, we are going to have Ke times 2 divided by m, everything under the square root sign. I believe this is easy for you guys at AS level. Now we can say V is equal to, we substitute the data that we have. For Ke, we have 0.16 multiplied by 2. For M, we know the weight, which is 2.5, and weight divided by G, it will give us 9.81. So 2.5 divided by 9.81, that is our mass. Weight divided by the acceleration due to gravity gives us the mass. If we substitute those values, we are going to get a rounded value, which is 1.1 meters per second as our speed. Let's move to question number 4. A spherical oil drop has a radius of 1.2 times 10 to the power minus 6 meters. The density of the oil is 940 kg per cubic meter. Show that the mass of the oil drop is 6.8 times 10 to the power minus 15 kg. Alright, this one, straightforward. We use density is equal to mass over volume. Therefore, mass is equal to density multiplied by volume. In the question, we have been given the density, but we have not been given the volume. However, we know that our oil drop is a sphere. We'll assume that it is a perfect sphere. So the volume of a sphere is calculated using the equation. We use V is equal to 4 over 3 pi r to the power of 3. Alright, now if we substitute the values, 4 over 3 multiplied by pi times our radius is 1.2 times 10 to the power minus 6, everything cubed. This is going to give us the volume. I suggest that you do not simplify this expression, otherwise you may lose some accuracy. So we will take this expression as it is, and we say mass is equal to density, which is 940 multiplied by this expression. So multiplied by 4 pi over 3 times 1.2 times 10 to the power minus 6 cubed. Let's punch these values in our calculators and confirm that the answer will come out as 6.8 times 10 to the power minus 15. Therefore, we have shown that the mass of the oil drop is 6.8 times 10 to the power minus 15 as required by the question. Alright. The oil drop is charged. Explain why it is impossible for the magnitude of the charge to be 8.0 times 10 to the power minus 20. Okay, looking at this question, I was thinking about dividing this value by the elementary charge, but I'm seeing that we are raising 10 to the power of minus 20, which is actually smaller than the elementary charge E, which is equal to 1.6 times 10 to the power minus 19. This is the smallest possible charge that we can ever have, in quotation marks. For now, this is the smallest charge that we can ever have. We know there are smaller charges, but for now, let's just work with this. So it is impossible because the minimum charge the minimum charge possible is 1.6 times 10 to the power minus 19 coulomb. Alright, so that's why it is impossible for the oil drop to have any charge which is lower than the minimum possible. Alright, there is Millikan's experiment. The charged oil drop in A is in a vacuum between two horizontal metal plates as illustrated in Fig 4.1. Okay, so we study our diagram. The plates are separated by the distance. The electric field between the plates is uniform and has got strength as shown there. The oil drop moves vertically downwards with a constant speed. Calculate the potential difference V between the plates. Alright, this is easy. We can use the equation electric field strength is equal to V divided by D. Therefore, V is equal to E multiplied by D. And if we substitute the values, the appropriate values, we see that our strength is in SI units, which is 2.1 times 10 to the power 5. And our D, it has been given as 8 millimeters. We are going to say it's 8 times 10 to the power minus 3. Therefore, the voltage in between, if we punch in our calculators, we will get 1.7 times 10 to the power 3 volts. So 1.7 times 10 to the power 3 volts. Alright. Explain how the motion of the oil drop shows that it is in equilibrium. Let's go to the question and see where the motion was mentioned. The oil drop is moving down with a constant speed. When speed is constant, it means there is no resultant force acting on the oil drop. Therefore, it is in equilibrium. So we can say it is moving constant speed. Alright, so that is our oil drop. Determine the charge on the oil drop. Very exciting experiment which was done by Robert Millikan, and let's just repeat what he did in that historic experiment. We know that the weight of our oil drop is the gravitational force of attraction on the oil drop. So mg, this is the weight of the oil drop. But Millikan balanced this oil drop in the air by adjusting the voltage which was across the plates. This voltage across the plates created an electric force which was pulling the oil drop upwards. So the oil drop is trying to fall down with a force that is equivalent to mg, but the electric force is pulling up with a force that should balance mg, and the electric force is equal to E multiplied by Q. This is the equation for electric force. So when mg is equal to E multiplied by Q, we saw that the oil drop would suspend. It would suspend in the air, or it will move down with with constant velocity. Alright, now once we have that, we can substitute the rest. So Q is equal to mg G divided by E. We have already calculated the value of M, and we found out that it is equal to, I think I forgot 10, let me just quickly check, 6.8 times 10 to the power minus 15. 6.8 times 10 to the power minus 15 multiplied by 9.81 divided by E. The value of E is, this is our value of the electric field strength, 2.1 times 10 to the power 5. Alright, so if we punch in our calculators, we'll get the charge is equal to 3.2 times 10 to the power minus 19 coulombs. Then what is the sign of the charge? Alright, let's get to our, okay. This charge, if it is positive, it would be repelled by the top plate. If it is negative, it would be attracted by the top plate. And using this argument that we drew here, we can see that our oil droplet is being attracted upwards. So this is a negative charge. Alright, the magnitude of the potential difference between the plates in B is decreased. Explain why the oil drop accelerates downwards. Okay, we know that if we reduce the potential difference between the plates, the electric field strength is going to weaken. Therefore, the electric force, as shown there, will become less. So that electrical force will no longer be able to balance the gravitational force, the weight of the droplet. Hence, it will accelerate downwards because there is now a resultant force. EQ is no longer equal to mg. In fact, mg is now bigger than EQ. So the oil droplet is going to accelerate downwards because the electric has been weakened. The electric force has been weakened. These are 2 marks. We need to include another point. And the weight is now greater than the electric force. So there is resultant. So there is resultant force acting on the drop. That is the reason why it would accelerate downwards. If there is no resultant, there will be no acceleration. Alright, describe the change to the pattern of the field lines or the lines of force representing the uniform electric field as the potential difference decreases. When the electric field strength becomes weaker, the electric field lines, they will become more and more spaced. In fact, the closer, let me just draw two plates here. Let's say this is the positive plate and this is the negative plate. If the field is very strong, we will have our field lines being very close to each other like that. With our field lines, the arrows always point from positive to negative. Let me just add that there. If our field is weak, same arrangement, we have positive on top and negative on the bottom. The electric field lines will be further from each other like that. So the field lines will separation, let's say separation of electric field lines increases. All right, that is what happens over there. Two types of force, X and Y, can act on an oil drop when it is in air, but cannot act on an oil drop when it is in a vacuum. Force X can act on an oil drop when it is stationary or when it is moving. Force Y can act on an oil drop when it is moving. This one, force Y is definitely drag, which is also air resistance. If a car is moving, if an object is moving in any medium other than the vacuum, it will experience a drag. Then force X, this should be upthrust. The upthrust, this force acts on an object that is immersed in a fluid, and we know that air is a fluid, so it will give upthrust to our object there. Let's look at question number 5. A loudspeaker oscillates with frequency f to produce sound waves of wavelength lambda. The loudspeaker makes n oscillations in time t. State expressions in terms of some or all of the symbols f, lambda, and n. Number 1, the distance moved by a wavefront in time t. Okay, so let me just draw a simple wave. All right, from here to here, this is a distance of 1 lambda. From here to here, this is a distance of 1 lambda. So we have 2 wavefronts that are equal to 2 lambda. In the case of our question, there are not 2 wavefronts but n wavefronts. So n wavefronts multiplied by lambda will give a distance of n lambda. All right, let's look at the expression for time t. Time is equal to distance over speed. So the distance that has been moved is n lambda, and the time to move that distance is equal to the speed of the wave would be f lambda. The speed of any wave is equal to f lambda. Now if we cancel out the lambda, we are going to have time t is equal to n divided by f. All right. Use your answer in 1 to deduce the equation relating the speed of the sound wave to f and lambda. They are basically asking for the equation of the wave. Speed is equal to distance over time. We have just seen that distance is n lambda and the time is n divided by f. This is equal to n lambda times f over n. Cancel out the n, we have our speed v being equal to n being equal to f lambda. So v is equal to f multiplied by lambda. That's right. Let's go to B. Okay, I was doing this with my students in the morning. So here we have the waveform of a sound wave is displayed on the screen of a cathode ray oscilloscope as shown in Fig 5.1. The time-based setting is 0.2 milliseconds per centimeter. So here on the x-axis, every centimeter, 1 centimeter is equal to or equivalent to 0.20 milliseconds. That is what our time-based setting is telling us. Now, if we look at one wavelength from this point to this point, it has got a period of 4 centimeters, so that's 4 times 0.2 milliseconds because each centimeter is equal to 0.2 milliseconds. So 0.2 times 10 to the power minus 3. So the period would be equal to 0.8 times 10 to the power minus 3. Okay, let's see. Yep, that looks good. So our frequency is equal to 1 over t, which is equal to 1 divided by 0.8 times 10 to the power minus 3. If we punch that in our calculators, we will get 1300 hertz. All right. Two sources S2 and S1 of sound waves are positioned as shown in Fig 5.2. The sources emit coherent sound waves of wavelength 0.85 meters. A sound detector is moved parallel to the line S1, S2 from a point X to a point Y. Alternate positions of maximum loudness L and minimum loudness Q are detected, as illustrated. All right. Okay. Our distance S1x is equal to distance S2x. Okay, S1x. All right. So this is our point which is directly in front of S1 and S2. Explain what is meant by coherent waves. The coherent waves are waves which have a constant phase difference. All right. State the phase difference between the two waves arriving at the position of maximum loudness that is closest to point X. Okay, position of minimum loudness that is closest to point X. Let's see. All right. So here the path difference between S1 and S2, the path difference would be 0. Here the path difference would be half of a wavelength. Here the path difference would be a wavelength. So the phase difference, when we convert our path difference to phase difference, we can say lambda divided by lambda times 360. Okay, for some reasons I am very interested in finding position of maximum loudness that is closest to point X, but the question actually wants the position of minimum loudness. So the position of minimum loudness is this point there. So it's 1/2 lambda multiplied by 360, which is going to give us 180 degrees. Remember the equations for phase difference. We have phi equal to t over period times 360. We also have phi equal to x over lambda times 360. And in this particular question, our x was equal to 1/2 lambda. Perfect. So first difference is 360, is 180 here. Determine the distance S1y. All right, let's see. Just delete that very quickly. All right, S1y, we are talking about this distance. That is our S1y. Let's use first difference to sort this out. First difference is 0, it's lambda, it's 2 lambda. We know this because the next maxima from the 0 order maxima is at a position that is lambda distance away. The second maxima would be at a position that is 2 lambda phase difference. So if we say S1y minus S2y would be equal to 2 lambda. Okay, the wavelength is 0.85, so S1y is equal to 2 multiplied by 0.85 plus 7.4. S2y is 7.4 meters. The answer that we get would be 9.1 meters. So S1y is equal to 9.1 meters. Now to question number 6. A battery of electromotive force E and internal resistance R is connected to a variable resistor of resistance R as shown. The current in the circuit and the potential difference, okay, or that information is given. Explain in terms of energy why V is less than E. We know that inside the battery there are components which resist the flow of current. And when those components resistance is put together, we depict that value as our R, which is the internal resistance of the battery. Now, when the circuit is complete and current is flowing, we are going to see a dissipation of energy whenever current passes through the resistor there. Here we are talking about the internal components of the battery which provide resistance to the flow of current. That energy is given as I squared R and is generally termed the lost energy. This lost energy gives rise to lost volts. So the potential difference generated by the chemical reactions there is supposed to be equal to this value plus this value. So V is less than E because of the lost volts within the internal resistance of the battery. State an equation relating E, I, R, and V. Okay, we know according to Kirchhoff that the potential differences across the circuit are equal to the electromotive forces generated within the circuit. So this is the electromotive force, and here we have a potential drop which is equivalent to IR. Here we have a potential drop which is equivalent to IR. If we put this together, E should be equal to the potential drops, which are I. Okay, this is supposed to be capital letter R, which are IR plus IR. So this is equal to IR. This one is equal to V, then plus IR. So this is the equation which links E, V, I, and small letter R. The resistance R of the variable is varied. The variation is shown as over there. Now the resistance was changed and the current changed in response. The potential difference changed in response as well. Let's see the questions. Explain how it may be deduced that the EMF of the battery is 2.8 volts. We have seen the equation E is equal to V plus IR. If we make V the subject of the formula, V is equal to I minus IR plus E. Now in the graph of V against I, this is similar to Y is equal to MX plus C. This C or the E is actually the point where our graph crosses the y-axis. And if we go to our diagram, we can see that our graph is crossing the y-axis on 2.8 volts. So we can deduce that the maximum the value of E, which is in this circuit, is 2.8 volts according to that equation. All right. Calculate the internal resistance R. Okay, the internal resistance R of the circuit again, according to this equation, we can see that R is the gradient. I think it was more clearer if I had written my equation as V is equal to minus R I plus E. This makes it even more clear. Now we can really equate to MX plus C. So this R is actually equivalent to the gradient of our straight line. Now if we go to our line, we'll just pick 2 points, and from those 2 points we can draw we can calculate the gradient of the line. So I'm going to pick this point and that point. This point is 0, 2.8, and that point here is 1.5 and 0.7. Now gradient will be equal to 2.8 minus 0.7 divided by 0 minus 1.5. Remember delta y divided by delta x. And from this, we are going to get our R is equal to 1.4. You actually get that it is minus 1.4, but we know our resistance, we will take the modulus. So it is equal to 1.4 ohm. All right, so that is our resistance, internal resistance, 1.4. The battery stores 9.2 kilojoules of energy. The variable resistor is adjusted so that V is equal to 2.1. Use the fig to calculate resistance R. Alright, so when our V is equal to 2.1, let's see what is the value of current. V is equal to 2.1 here, and current is equal to 0.5 at the bottom there. So we can say R is equal to V over I, and this is going to give us 2.1 divided by 0.5. If we punch these values in our calculator, we will get that our resistance is 4.2 ohm. So that is the resistance of the external resistor in our circuit there. Let me put it here, 4.2 ohm. Calculate the number of conduction electrons moving through the battery in a time of 1 second. All right. Okay, so we know that electric current is equal to charge passing through a point divided by the time for the charge to pass through that point. Now this Q is actually equal to the number of charge carriers multiplied by the charge on each carrier. So in this case, we are talking about a conductor where the charge on each carrier, or the carriers are electrons, so the charge on each carrier is the elementary charge, which is 1.6 times 10 to the power minus 19. So if the current is 0.5 and the number of electrons, let's just say it's n multiplied by 1.6 times 10 to the power divided by 1, then n would be equal to 0.5 divided by 1.6 times 10 to the power minus 19. If we punch these values in the calculator, we will get our n being equal to 3.1 times 10 to the power 18. So we have 3.1 times 10 to the power 18 electrons, which are passing through a particular point in a time of 1 second. Determine the time taken for energy in the battery to become equal to 1.6 kilojoules. All right. So we have the energy right now minus the energy when we get to 1.6. Let's just call it 1.6. This is equal to the equation of energy is E multiplied by current multiplied by T, and this E is actually the EMF. All right, so this change in energy is the initial is 9.2 kilojoules, and the final is 1.6 kilojoules. So we can say 9.2 minus 1.6 kilojoules equal to the EMF of the battery. The EMF of our battery is equal to 2.8. I think it was 2.8. Yes, 2.8 multiplied by I, which is the current flowing. The current flowing through this is 0.5 multiplied by the time taken by the current to flow. So if we make T the subject of the formula, 9.2 minus 1.6 times 10 to the power 3 divided by 2.8 times 0.5. If we punch this value in our calculator, we are going to get 5.4 times 10 to the power 3 seconds. So this is the time which is taken by the battery to move from that amount of energy to 1.6. Now to the last question, number 7. One of the results of the alpha particle scattering experiment is that a very small minority of the alpha particles are scattered through angles greater than 90 degrees. State what may be inferred about the structure of the atom from this result. Alright, so this is very interesting topic, and I encourage you guys to read through everything on this topic as required by our syllabus for you to have a good time in the exam. Otherwise, there is very little reasoning that you are given very little room to reason around. They actually are very specific about what they want when it comes to questions in particle physics. So the fact that very few particles are being scattered means the nucleus is very small. If the nucleus was big, a lot of particles were going to be scattered backwards, but it is very small, so we are getting few particles being scattered. Then secondly, this scattering is happening because the nucleus is charged. If it was not charged, the other particles, charged particles like alpha particles, were going to just whiz past the nucleus. But now the nucleus is charged, so as the alpha particles approach it, they start to feel a deviation, and they are deviated away. So we know it's charged, and we can even tell the charge. So we can also say the nucleus is charged. So these are the results that we can get from the alpha particle scattering experiment. A hadron has an overall charge of plus E, where E is the elementary charge. The hadron contains 3 quarks. One of the quarks is a strange quark. State the charge in terms of E of the strange quark. Okay, so the charge of the strange quarks is minus 1 over 3 E. That is the charge of the strange quarks. The other 2 quarks in the hadron have the same charge as each other. By considering charge, determine a possible type or flavor of the other 2 quarks and explain your working. Alright, so the strange, which is minus 1 over 3 E, plus 2 other particles, which we are going to say 2 multiplied by their charge, which is X, is equal to E. So if we do our math right, we will find that the other charge is equal to 2 over 3e. And from the work that we have done, we know that this is the charge of the up. You can call this an up, or you can also attribute this charge to the top or to the charm. So this is our paper, guys. I encourage you to work very hard and see you next time.